skip the code. So I want to cover arithmetic and then some other weird errors that we're going to come across. This is a small enough slide set. We'll do this. I have another example to give you and to get you work through some arithmetic, and we're going to go from there. And now I'm live. Hooray! Okay. So far, we've seen two types of printout statements. We've seen system.out.print, and when we have system.out.print, it will take whatever content we're printing out, we'll put it there. And if we run another print statement after it, it'll print it on the same line. And then we've seen system.out.println, where we have our statement that we print, and it moves the cursor. When it's finished printing this bit, it moves the cursor down, so the next print statement we have appears underneath it, okay? You can use a combination of those to get the output you want, or the layout you want from your programs. There are more to come. There's one specifically called printf, but that doesn't make sense until we've covered variables, and then we'll loop back around to kind of cover that. Okay, we covered that already. It requires you to use special inline commands. Okay, this is basically recapping or doing the slides and the backslash thing. So we have this idea of a legal or of an escape character. The backslash is considered a special character. When we have the backslash, it means the next character is going to give you a command to carry out. For example, \t gives you a tab space. So here are the most common ones, and I'm aware that in this long room that actually might be hard to read. But I'll highlight the ones that are important for us, the ones that we actually use. The top one here is \t. That inserts a tab space. So it'll just shuffle along the cursor by usually 4 spaces in an operating system. We can ignore \b, we never use that. \n will bring you onto a new line. So that means it'll just drop you down onto the next line. It's the same as having a system.out.println command. \f we don't use. \apostrophe will insert a single quotation character or just an apostrophe into your text. So if you wanted to say owns class, print that out like EOIN apostrophe S class, then you would need to have \apostrophe, otherwise it would cause issues. The same with quotation marks. If you wanted to print an actual quotation as an output from your screen, you'd need to have the quotation marks you want to print on the screen preceded by a \, and then the one we ended up using, a double \, prints one \, on the screen. You're not going to come across them a huge amount, but you will occasionally, they'll pop up. And usually where they pop up, and the reason why I cover them this early, is next week you're getting your first piece of assessment from me. It's a workbook that will take approximately 6 weeks to complete. Each week we'll cover a new topic, which means each week you'll have one new question you can do in that workbook. Okay? So it's a 6-week assessment, but the amount of work required each week is something that's absolutely achievable within the class time to get it done. But then after the first workbook, you'll be issued your first take-home assignment. It's a 2-week take-home assignment, and that in the past has been a game of some description. And I'm focusing on if statements and loops and variables and user input and printouts. None of the stuff we've covered. We've covered printouts, but nothing else. And students, because it's a game, like to make it visual, give it a nice interface. And so they might have characters on the screen or try to do ASCII art to print out stuff on the screen using the characters on the keyboard, and that's where they run into the \, or I want a quotation mark, or I want something else. And that's why I covered this now, so that, at least from that point of view, that's where I've seen students come across it. But you will see this as you go further into your programming career. Okay. Let's move on to the body of this. Calculations. Computers are exceptionally good at doing calculations. I'm aware the last example I did in the board has assigned saying computers are stupid. And I stand by that. They are stupid. They can do a very limited amount of things compared to you or I. However, what they can do exceptionally well is they can follow mathematical calculations. Okay? They don't make mistakes. They don't get lost. They're able to do repetitive calculations without getting distracted or bored or frustrated or agitated. The things which we suffer from. Okay? If you give them the correct formula, they can solve problems generally way faster than a human. And the more complex the problem, the slower the human is at solving it, but the computer kind of maintains the same speed. There is a module in third year you're going to cover called numerical optimization, where you will actually look at the correctness of calculations. You will be able to calculate how many processor cycles your code should take. And the point of doing this is to work out that you have the most efficient code, the code that runs in the smallest amount of space on your hard drive. It uses the smallest amount of working memory in your machine, the RAM in your machine. It uses the smallest amount of processor cycles. It's as small as compact as possible. And you'll look at how you can take a mathematical formula which looks really, really complex, but you can actually calculate, oh, this will only take 3 time units to complete. And the reason why you know that is because you can say, well, that's each action is a specific amount. It doesn't matter if it's all the calculation is really tough or the multiplication or we get lost there. You and I as humans, and I'm sure you're going to run into this through foundations of computing, you're going to get lost. You're going to start off a tangent with, let's say, balancing an equation. And you go, oh, no, I shouldn't have done that there. I should have done. I made a mistake and I kept going and the mistake got worse and worse and worse and worse. And so I have to find the point where I made that mistake and go back to there and fix it from there. Computers don't do that. If you give them the correct formula, they follow that formula exactly. They have no intuition, they have no common sense, they have no distraction. So they just follow through. So what we need to do is we need to figure out how we can get our program to do calculations. And for the moment, until we hit the end of today's lecture, we're going to do all our calculations in that printout statement. So what will happen is it'll take the inside your brackets, the system that out the print, it'll go, oh, I can make this simpler. And it'll solve the calculation for you, and then it'll put the result out on the screen. Okay, we have several basic operators. We have brackets, we have addition, subtraction, multiplication, and division. Addition, subtraction, multiplication will work exactly as you expect it to work if you were doing this with pen and paper or a calculator. Okay? The symbols we use, addition is the plus symbol, subtraction is the minus symbol. For multiplication, we use the asterisk to multiply 2 numbers. So 5 asterisk 10 is 5 multiplied by 10. Division is a little bit tricky, and I'll explain what happens and why it works that way in a moment. The one you mightn't have come across, or the one that we haven't used this huge amount in pen and paper mathematics, is brackets. And it goes back to, if you remember from secondary school, the idea of BODMAS, that you have a certain order of precedence that calculations work on. So you've got brackets, then you've got orders of magnitude, so like your exponent, then you've got division, multiplication, addition, subtraction. And so it'll follow that way through it. Now, if they're all the same, so if they're all the same precedence, so if you've got 1 plus 5 plus 7 plus 8 plus 9 plus 10, it just goes to the left-hand side and works its way across. Whereas if you've got 1 plus, and then you have brackets, and then you have another calculation inside the brackets, and then you have plus something else, it'll do the bit in the bracket first, and then it'll go back to the left-hand side and work its way across. I'm going to get down to division in a moment. So here's an example. And since the code is actually live at the moment, if you can't read it from the back, I'd say either log into the YouTube channel or open up the notes. So here we have 2 plus 2. Okay, very, very simple, just an addition. The way this is going to work is it starts with, it finds the number, the first number, which is your operand. It finds the operator, what mathematical symbol you have, and it finds the second operand or the second number. And it goes, oh, okay, I've got number, operator, number. I know what to do with this. And it can simplify that equation. It solves that. It replaces 2 plus 2 with the answer, 4. And when it can't simplify that anymore, when it's got what's called a literal value, 4, it'll just print that to the screen. What will happen here in the second one, we've got 2 plus, and then we open our brackets, and we've got 10 minus 7, close our brackets. Is it'll go, okay, 2 plus, oh, this is in brackets. It'll take this part and solve that next. So 10 minus 7 gives us 3, and it replaces 10 minus 7 with the value of 3, and then it goes 2 plus 3, which will then replace it with the value of 5. And then when it can't simplify it any further, it will print it to the screen. So this idea of replacing it, I can make this simpler. I can make this simpler. And once I've done that, I can make the whole thing simpler. That's something called a substitution rule. Whenever you are running a program and it can identify that I can make this simpler. At the moment, it's just actually solving calculations. But what we're going to see after the break is when we're looking at variables, then making it simpler is if I've got a storage area where I'm going to hold the results of this calculation, I can replace the word I'm using. So let's say my result is what I've called my variable. I can replace that with the actual value. and I try to simplify and simplify and simplify the equation until I get my result. And then you can have something like this, where you've got 2 plus 10 minus 7 multiplied by 13. But because you've got brackets here, you're forcing it in a certain direction. So you're forcing the innermost brackets first, so it's 10 minus 7, leaves us with 3. You're then forcing the next set of brackets, which will be 3 multiplied by 13, which gives us 39. And then when all of the internal brackets have been solved, we're then going to say, well, the result of that, 39 plus 2, so our output should be 41. Does that make sense? Okay. For those of you who can read the last line, what do you think is going to be the output of that? And I'm aware the font isn't fantastically big. Hang on, let's see if I can make it larger. Maybe what? Oh, no, well, that's it. Let's go with 22. Okay. And it's slightly bigger, not huge. So, can anyone see any issue with that? It's missing one bracket, exactly. So you can see here, and again, it was a bit obvious to see, but yes, we open here, we open 1, we open 2, we open 3, we close 3, we close 2, we close 1. Every bracket has its match. Here we open 1, we open 2, we open 3, we close 3, we close 2, and we're missing the closing bracket for our first pair. These type of things are going to pop up every now and again. You need to be really careful as you're writing programs, and as your programs become more complex, and as you use more brackets in your programs, that whenever you open one up, you make sure that you close it as well. Second most common problem, most common mistake that I see in people beginning programming and first year programmers is missing brackets. And you'll either get some weird error where it crashes there, or if you leave one of the closing brackets off here, you'll get the error which is reached end of file while parsing or whilst parsing. And that basically means your closing bracket for either your main method or for your program is missing in it. It got to the end of the file, there's no more code, but I haven't received the bracket to say, hey, this is the end of the program. And so that's why you get that error. So yes, the missing bracket there is what was the issue. Okay, brackets are really, really important. Is it a best case scenario if you miss a bracket is that your code will actually not compile. Now that sounds like a bad thing, but if your code doesn't compile, it gives you an error message. Hey, this isn't working. Fix it. You know there's a problem. Now, that's not much consolation if it's the night before an assignment deadline and you're desperately trying to get something up and running. However, it's much better for the missing bracket to tell you it's broken, it's not going to work, than for the missing bracket to pick up another bracket somewhere else, or maybe you've missed a second bracket. And now your program works, but in an unexpected way. And you'll compile it, and for anything you submit to me, I would always say the very last thing you do before you click upload on Moodle is you compile it and make sure you're giving me software that compiles. Okay? Even if you have to comment out a huge section of code, the bit that wasn't working or the bit that was still a bit broken, if you send me code that doesn't compile, that causes an error when I try to compile it on my machine, not for the workbook, but for every assignment, there are marks docked off that because you shouldn't ever give anybody code that doesn't compile. You might have to cut out or comment off a huge chunk, and the functionality might be kind of quite broken, but it should compile. It shouldn't give you any errors like that. And that's a habit that I want to build into you now, so that as you go forward in the second year, third year, and fourth year, and you go out into your careers, that you know, well, look, I will never give you code that doesn't work or that doesn't run. You will always be able to run the code, and I will always highlight what I wasn't able to get complete or what I wasn't able to get done. So you need to be very, very careful with brackets. Let's have a look at how brackets can mess up or change how calculations work. So what I'm going to do is I'm going to take New one here. Nope. That's it. I'm gonna go new file. See. Question one. Let's do that. Actually, we'll go back here and take all of these codes. Okay, so here's our outputs. If I spelled it right, it would help. Question. Oh, Java. Okay. So what I'm going to do here is I'm actually just going to delete all the brackets that are superfluous. We don't need to go here. Okay, so what should happen when I run this is it'll run the first one, fine, they're simple, it's one operator and two operands, so it's a number, a symbol and a number, it'll solve that pretty quickly. It should do this one pretty quickly, and as we expect, it'll do the inside brackets first, it'll simplify that to 3, and then it'll go 2 plus 3, and it'll simplify that to 5, and print that out on the screen. What was the third line of the slides, I put the last line here, where it has all of the appropriate brackets, and here the output should be 41. We're going to get 10 minus 7, which gives us 3. 3 multiplied by 13, which gives us 39. 39 plus 2 gives us 41. And then I've just removed all the brackets. And I've got multiple symbols in there. So it's just a highlight that you can have the same technical calculation, same numbers, same symbols, but without the brackets, you'll end up getting different results. So let's run this and see what we get. Let's save that code. Command prompt. I'm going to run Java C. Lab question. Came back okay, good. And then Java lab question. Okay, so here are my outputs. I have 4, that's good. I have 5, that's good. I have 41 as the last output, that's good. They're all the expected ones. But by taking the same calculation and removing all of the brackets, my output for line number 5 is minus 79. Okay, it's not ideal. We don't really want that. So what we need to do is we need to make sure that if you know how the calculation works or how you want it to work, you can add in brackets to force the program to calculate it that way. Okay, that's one way you can use brackets. Another way I personally use brackets, and you'll see that in the example we're going to do in a moment, is I put in brackets for my own visual aid. Okay, so I could have, actually in all those examples it wouldn't necessarily work, but let's go back to my slides for a moment. Now, this is the example we're going to do here. All right, so that's a reasonably complicated calculation. One thing actually worth noting now, here's the mathematical compilation, mathematical formula for working out the area, the surface area of a cylinder, okay? 2 pi or h plus 2 pi or squared. In maths, in pen and paper maths, if we go 2 pi or h, it implicitly means it's 2 multiplied by pi, multiplied by or, multiplied by h. In programming, we have to be explicit with it. We have to put in that multiplication symbol. If you don't put in the multiplication symbol, you get very odd answers. Okay, so I'm going to work through this, and I'm going to put this out on the screen. This is actually a really good example. What we're going to do is we're going to look at this, and then I'm going to hop out to another problem that we're going to work through, where we're going to take this one, and we're going to take a volume of the cylinder, and we're going to take another calculation on a cylinder, and we're going to do all of them, just so you can see how math calculations work. Generally, for the last, this is my 9th year teaching first year programming. and I cover from what we did in week 1, just hello world, what's programming, to what we're going to teach in week 24, which is here's a collection of numbers. I want you to sort them into ascending order. If you don't have alphabetical numbers, into ascending order numbers. Write them to a text file with prime numbers, descending prime numbers of how many numbers per line. Really complicated problems that involve a lot of math. This is the thing that students hate most. When I give you a math formula that you would have seen in secondary school. I don't know what secondary school teachers have done to all of the students that I have ended up receiving, but I can get you to, I have got students to build me the game Battleship in Java. I've got students to build me Hangman. I've got students to build me Ludo. 1 year we tried doing Dungeons and Dragons, and they were fine throwing themselves into thousands of lines of code of that. This is a single printout statement, and this upsets students far more than a 3-week team assignment where you have to build a fully functioning role-playing game.
Battleship sounds more fun.
Then this? Yeah. We'll get there, but you have to do this first. You're in your stripes. Okay, so let's have a look at how we do this. There's no point in doing that. You can't see that. So let's do this here. Make that large again. And I'm going to save this as lab question 2. Lab question 2. Okay, so I shouldn't delete all that. I just need that much gone. So I need to set some baseline for this. I need to know what the values are. So for this example here, I'm going to say that for pi, we're going to use 3.1415. It's much, much bigger number than that, but that's enough for us to get working with. For the radius, I'm going to use 4.25. And for the height, I'm going to say we're going to use 8. Okay, so it's kind of a box shape or an equal width and height cylinder. Okay, the width from edge to edge at the top is 8.5, and the width from top to bottom will be 8. So it's almost like a square, a cube shape in cylindrical form. And for pi, we're just leaving it to this accurate here. So when I have all of those values there, the calculation is actually really simple. I understand, and I remember from my time at secondary school, it is a pain in the backside doing this pen and paper. But when all you need to do is feed in the correct numbers. What's or? Well, I'm going to put in 4.25. What's h? Oh, I'm going to put in 8. What am I using for pi? I'm going to put in 3.1415. It's just a matter of writing out the calculation, matching what the official formula is. And once you do that, it kind of flies. So let's have a look. Our formula, because I've forgotten it already, is dash. So let me write the formula. We are going to write, and what I will point out here is we have 2 parts to this. We have the left-hand side, and we have the right-hand side, and we have a plus symbol in between them. On the left-hand side, it's 2 multiplied by pi multiplied by or multiplied by h. I'm going to put that whole part in a bracket, and then I'm going to have a plus symbol, and then I'm going to have the left-hand side, which is 2 multiplied by pi multiplied by or squared, which is actually for us, because we don't know how to do exponents yet, it's going to be 2 multiplied by pi multiplied by or multiplied by or. Okay? Because or squared is just or multiplied by itself. So what we're going to have here is we're going to have 2 multiplied by 3.1415 multiplied by, that's 4.25 multiplied by, once I get the formula in, I'll make the screen full so you'll be able to see the whole thing in one go. Multiplied by 8, and that should be in more brackets. So bracket there, and it's going to be plus, open my brackets, close brackets, and this is going to be 2 multiplied by 3.1415 multiplied by 2.4 multiplied by 4.25, close brackets. Okay. Again, Notepad++ is wonderful. If I click on a bracket, it should highlight both the opening and the closing of that bracket in red. So I should be able to see how this is working. And the most important one, they close there. Right. That is my formula translated into that calculation. At this point, me as the human, I'm done. I can save my code. So I've written my code, I can save my code, build my code, run my code, and give you the correct answer. If my formula matches to the correct formula, and I've written the numbers incorrectly, so I haven't mistyped any of those numbers, it should work perfectly. I don't need to worry about doing the calculations. I don't need to worry about anything except just running the code. So let's have a look. Now, here's a really good example of where some students fall down a rabbit hole. I set a workbook, or I set an assignment, or I give you a challenge in the class, and the really enthusiastic students jump ahead and start typing out code. And the more content we've covered, the more comfortable you are throwing yourself at a problem and really typing it out. I don't know off the top of my head what that answer is. Do you? No. Thankfully, we've Googled, so we can look it up. But the key point here is, if I've given you specific values, which we have over here, can I do? I think I can actually just do that. Keep it all on one screen. If I've given you specific values, what pi will be, what or will be, what 8 will be, sorry, what h will be, I may as well put this into a calculator to see what my end result should be. So I know what my expected outcome is. It is really, really important as you go into the journey of programming, and as your programs get more and more complicated, more and more detailed, you should know, as a developer, what the output should be. If everything goes smoothly, what's it going to print out on the screen? It worries me when we hit kind of week 8, week 9, week 10, just as we get to the end of the first semester, and the student comes down, oh, I have a problem with this. And I go, okay, what should I do? And they go, I don't know. That worries me, because it means that you've been sitting there for a period of time, and you've been typing away code, and there's lots of code on the screen. You're not 100% sure what's meant to be the output. So what I will say going forward, next week, as I said, I'm going to give you your first piece of graded assessment. If you don't understand the question, get a clarification. Ask me, what does that mean? Get me to re-explain it. Get me to give you another example so you can see what is expected of you. It's really, really hard to answer a question, to submit some work for grading, if you don't know what's been expected of you. So for me, and for any of your lectures, if you don't understand what you've been asked, ask. It's much better to swallow your pride a little bit and go, look, I don't understand what you're asking me. And get it explained and go, oh, okay. And then use the rest of that time to correctly answer that, than to stay quiet and guess at what's been asked. Okay? So I don't know what the answer to that is, but I'm going to feed it into Google and see what Google gives me. So Google is wonderful. Google can give me, that is the surface area of a cylinder. There we are. You can see I've been doing this a lot this week. As well as giving you the formula, if Google wants to work, Google gives you an interactive formula, eventually. Right, well that's working in the background. I'm just going to compile this program to make sure it's actually working. So I'm going to save the code. I'm going to go here. I'm going to lab question 2, compile the code. Good, that's working. And then I'm going to go lab question 2. I don't run the code. And my answer is there. It is 327 point and then a whole load of values after that. Have I got Google working it? Yes, excellent, right. So what Google gives you, which is wonderful, and they do this for nearly any of those kind of volumetric formula you need to look at, is they give you an interactive example. They give you the formula. But what I can do is I can say, well, 4.25 there. It's highlighting. Okay, 4.25 is going to be put into these places here. And my other value is 8. And it gives me the calculation. Now, let's have a look. That's 327.12. And I've got 327.1086, blah, 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 blah. And we're rounding that will become 1.1. Why is there a difference in my calculation to Google's calculation, do you think? Because of pi, exactly, because of pi. I'm using 4 digits of pi. If I were to open up Google as well, I'll just type in pi, it would tell me pi is that. Okay, and that's 12 digits, to make it much more accurate. If you can see this picture here, that's pi, I think, to a value of like 150 decimal points, or points of accuracy in decimal. So it gets really, really, like it's an infinite number. The decimal end of it keeps going. That's what Google uses their reference for their calculations. You don't need to. If I ask for pi in an assignment or in a class test or in an exam question, I will tell you what I expect pi to be, 3.1415 or whatever amount I give you. But if I were to take this value here, copy that, go back to my code, and replace that, and replace that, save it, back here, rebuild it, run it. Where's Google? There. No, 8. So you can see now I've got 3.27, that hasn't changed, 1.1.8 by that. And if I were to round it down to 2 decimal points, that would become 0.2. So it matches the calculation. Again, we verified our calculation is correct. Now, the downside of all of this is even not using that, even using small value pi. That's a lot of numbers. That's a lot of specific numbers, but they're repeated. So pi is repeated twice in this calculation, 4 is repeated once to 3 times, 8 is in there once. And that's just for one calculation. What we're going to see after the break is that we have a much more efficient way of dealing with this, of running with this type of question. The other thing I want to highlight here is for me personally, because 4.25 multiplied by 4.25 is meant to be r squared, what I generally do when I write this code is I add in an extra set of brackets. Those brackets are functionally useless because on this side of the equation, everything's a multiplication. So it doesn't matter what order you do it in, it ends up with the same answer. But for me as a visual aid, when I'm using an exponent, whether it's a square or cube or whatever it might be, I like to have it inside a bracket because it just visually says, oh yeah, that's where we're getting our exponent from. And then the rest of it is the other part of the calculation. We will get to a math library where you can just say 2 to the power of whatever it might be and we'll do that calculation for you. But we haven't covered that yet, so we're looking at it this way. Does that make sense? Do you guys have any questions at this point for me? Or will I move on with slides for another 10 minutes or so before we take a break? Okay. And on the break, what I'll do is I'll put up this code and I'll put up all the previous code and categorize it, and just so that you have a reference point for when we have to do some work after the break. Okay, so print the screen. Okay, so I gave different examples there. But you can see what's going to happen is we're left with a calculation that looks at this. And even here, even though I've done the calculation backwards, I've done the left-hand side first, or sorry, the right-hand side first, then the left-hand side. That's my r squared there. And so I've even put it inside brackets. Yeah, that's basically what we've covered there. Now, I'm going to leave you with this before we take a break, and this is, again, something that gets confusing. We've talked about addition, subtraction, and multiplication. And for the most part, they work exactly as you would expect them to work. Division, however, is weird. Inside programming languages, we have what are called data types, what the second half of today's lecture is going to look at. And those data types hold different types of information. You can have a Boolean data type that only holds true or false. You can have a character data type that holds a character you can type on the keyboard, whether it's a letter or a number or a symbol. You can have a numerical data type that holds a number. And inside numerical data types, you can have a real number, so it's got a decimal point in there, or you can have what's called an integral number. It is only a whole number. And if we've got the possibility of only having a whole number, that causes a lot of confusion and difficulty for division. If you take two whole numbers, 7 and 2, and you divide them, 7 divided by 2, you're left at 3.5. But if we're only dealing with whole numbers, what are you left with? Or 3. Which one is it? So it's basically what they have done is they have split division for when you're only using what are called integers or integral numbers. They have split division into two different calculations. How many times does it go in evenly? And what's the remainder? Okay, and these two are called the div command, which is a /, and this will tell you how many times that number will go in evenly to the other number. So for div 3 says, well, if I divide 3 into 4, how many times does it go in evenly? And that will give you whatever number it is. Okay, in this example here, it'll give you 1. Now we know it's not 1, it's 1.33333, but we don't have decimal points. We only have whole numbers, so it just gives you the whole number part. There was, I'm trying to remember the name of the episode, but there was a Simpsons episode where Lisa develops a cure to bullies, or a way of people hiding from bullies using pheromones. And it's causing uproar in the convention she's showing it. And Professor Frink tries to get the attention of all the scientists. The way he does it is by shouting, pi is exactly 3. That's effectively what happens when you use the div command. Even though the stuff on the right-hand side of that decimal point, the decimal end of that calculation could be really, really important, you just chop it off and you get rid of it. If you've seen the film Office Space, they kind of take advantage of that as well, in a poorly implemented way. But yeah, they kind of take advantage of that by skimming off the numbers that they feel aren't important and putting it off into an account somewhere else. So that's our division. So if I were to take, let's say, 10 div 3, so how many times is 3 divided into 10? I get 3. There's stuff left over, but I don't care about that. The div command, the / command, only works on how many times it goes in evenly. Now, if I had two decimal numbers, if I had 4.0 and 3.0, I get 1.33333. I'll show you that actually. I'll put it in this code in here, but I'll separate it into a separate program afterwards. Okay, so here. If I go 4.3 or 4 div 3, that'll give me 1 as an output. But if I do this, where I put in the decimal numbers, so I'm forcing the computer to use decimal numbers, it will give me the full and proper answer. Save that. Here. So you can see we're getting 1 when it's just div and we're using whole numbers. And then once we put in the decimal points in those numbers, it gives us point blah, 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 blah. Okay. Back to the slides. So if I have a way of doing the whole number division, I probably need a way of figuring out what's left over afterwards. And that's where the second command comes in, which is called the modulus command. And the modulus command will only concern itself with what's left over. It doesn't care how many times it divides in evenly. It's concerned with what's left over afterwards. So example I have here is 5 modulus 3 leaves you the answer 2. 3 will go into 5 once. We don't care about that. But 2 is left over afterwards. In any example, when you do run this, whatever value you have here, the number here will be somewhere between 0 and 1 less than this number. Okay, so let me give you an example. If we have 5 mod 3, we're left with 2. 6 mod 3, we're left with 0, because 3 divides into evenly with nothing left over. 7 mod 3, we're left with 1. 8 mod 3, we're left with 2. 9 mod 3, we're left with 0. So it goes 0, 1, 2. So it goes all the way up to 1 less than this number, but not up to it. If we did 5 modulus 4, we get 1. 5 or 6 modulus 4, we get 2. 7 modulus 4, we get 3. 8 modulus 4, we get 0. You see that pattern? So when you're wondering how modulus works, it will give you somewhere between 0 and 1 less than your divisor in the range of values. And it'll keep cycling through that. As soon as it gets to a point where it divides in evenly, completely, like 4 divided by 8, no, other way around, 8 divided by 4, then our remainder, we still get a remainder. The remainder is 0. Now, I am aware that all of you have got all the way through secondary school and you're here now in third level education, so division is something that you should be comfortable with. I'm also aware that this seems a really weird way of doing it. Even if you got over the point of fine, some computer programs won't use decimal numbers. It does seem a very odd way of doing it. But there are some really good advantages to doing this, some interesting things you can do. If you know, for example, modulus, that your remainder will always be from 0 to 1 less than the number you're dividing it by, you can calculate things. If I had 5 modulus 2, not modulus 3, but modulus 2, it would give me a remainder of either 0 or 1. If the remainder is 1, it guarantees that the number I'm dividing into, the bigger number, is an odd number. If the remainder is 0, it guarantees it's an even number. And so that would allow you to create a program where you could quickly sort odds and even numbers by using this calculation to say, well, what's the remainder? If I divide 2 into it and nothing is left over, well, then that's an even number. If I divide 2 into it and something's left over, well, then that's an odd number, and we can work our way through that. We will use the modulus command for a couple of programs. Not a huge amount. Again, there's other stuff to look at. And if I dwell just on the mathematical elements of programming, you'll be really good at that, but you won't be able to implement functional programs. So we'll dip in and out of it. 2 examples where I'm going to use this. One I'm going to do after the break. I'm going to take a multi-digit number. So let's say 123,000. No. That's the number, the 5-digit number. 1, 2, 3, 4, 5. 12,345. That's what I was trying to say. And we will split that up into its component digits. So we'll print 1 on one line, then 2, then 3, then 4, then 5. And then once we've done that, we can enter any 5-digit number, and we can split them up into first digit, second digit, third digit, fourth digit, fifth digit. Another way where we're going to use it is we're going to look at prime numbers later on in this course. We're going to look at how can you take a number in and tell me if it's a prime number or not. And we're going to look at 2 ways. The first way is what's called a brute force check. Does anyone here know what a prime number is? So a prime number is a special number that is only divisible by itself and by the number 1. So for example, 7 is a prime number. I can divide it by 1, I get 7, or I can divide it by 7, I get 1. 6 is not a prime number. I can divide it by 1, by 2, by 3, and by 6. Okay? Now, when that starts off, the first couple of numbers are really easy to work them out in your head. But as it gets bigger and bigger and bigger and bigger and bigger, it gets exceptionally hard to figure out whether a number is prime or not prime. A brute force check is you start at the number 3, because there's no point in checking 2, because after the number 2, no other even number is prime, because 2 divides into all of them. You start at the number 3 and work your way up to half of whatever number you're trying to check, and you're checking to see, do any of these numbers divide in evenly? And if they don't, well, then you find a prime number. If they do, it's not a prime number, move on to the next one. And so that's a really repetitive action, but we're using this command here. But we'll come back to that. We have to do user input, which is next week. We have to do variables this week, user input next week, if statements the week after, and loops the week after that. And then we can look at attempt on that. So there's a couple of weeks away. You have time to get more practice in. It is now just about 7:45. You want to take a 20-minute break, get some coffee, and we'll come back. We'll look at how to split up our 5-digit number into individual digits, and then we'll look at the idea of variables, and we'll go back, and we will go back to our soup tin question, or our cylinder question, and the splitting the numbers up, and use variables to show you how we can kind of improve our code. Okay.